Today is the 22nd, 22/2. Okay, we started heptane and water. So there's heptane and water. Heptane and water. Then we're going to do limestone and water. Hey, there's a couple. Hello, Sarah. Hello, Lily. Just thinking about what I'm doing with you guys today. Drawing some more little pictures. Hello, Julian. Welcome, 10E. Okay, so you can see the whiteboard a little bit. More important than me. Good. What else did we do last time? We did NaCl in water. We did ethanol in water. We did light dissolves light. We talked about hydrogen bonding. And yeah, we started heptane in water. Okay. Good. Who else I got? There's some more coming. I believe. How about you three? You doing okay? You got any questions about last time? Drawing lots of strange drawings? Everything going okay? You're on a Monday morning? Hope so. Hope we get a few more. 4 is not very many. And I got only 3 of the 4 responding here. There's another. Tom is here. Good. The world is safe. Tom is here. All right, so let's just write who's not here. Should not be here. And everything makes sense. Good. Glad to hear it. That is good. I'm just writing people I know will not be here. Anybody else there? We're going to take a couple more minutes, but I hope others show up. You should all be here. I did announce it, so that's kind of strange. But I will definitely have class, and they'll just have to watch it. And tempted to give them less points for that, but anyway. 35, that's pretty much enough time. Tell your friends, text your friends, I don't know. Hope they'll get here at 37. Ah, that's true. I forgot, Sarah. That's right. Okay. That's right. It's 10:37, isn't it? Thank you, Sarah. I've done so many 11:30 classes, I kept thinking it was at 10:30, so we still got a couple minutes. Okay. I'll relax. I'll try not to stress out. Hope none of you are stressing out. Then I'll go back to my list and take a chill here. We still got time. And you guys are just extra early. I appreciate that. Noah's here. Very good. That is swell. And Shilpa's here. Very good. Just checking people off. Swelleroonie. Can I ask you guys while we're waiting a question? How many live streams do your other teachers do? of our 4 hours, I want to do at least 2 per week with you. Are they doing about half of your class times with you? So how much are your other teachers doing in terms of live meetings with you? Thank you. Others, I got Tadashi and Nicholas. Great. I got Natalie. Very good. I got Riley. Dynamite. So question for everybody as we're gathering up. How many live streams do your other teachers do? Do they do about half of your hours that you meet, or more or less? I'm kind of curious how they're doing as well. Usually about half of the real classes are calls and the rest are assignments. Okay, Shilpa, so I'm trying to do the same thing. It's what they kind of told us to do. Vincent, thank you, good. And Priya is also here, super, thank you. Good, and Sarah adds, we usually do 1 Google Meet a week, but math may have 3 a week. Okay, all right, good. Isabella's here as well, Dynamite, good. Everybody's coming, I'm happy. Things are A-OK. The numbers are increasing. I love it. There's Magdalena and Julian K as well. Good. Dynamite. Nah, they're just cruising in. There's Lee and Larissa. Hello, Lee. Hello, Larissa. Nice. Good. Boom, boom, boom. Boom, boom, boom. Boom, boom, boom. Did I get? Yeah, I did, right? So I have no Aiden. I have no Lena. Lena out there yet? And Deacon, looking for Deacon. Looking for Ali and Dominic. Better call and get them out of bed. Okay, then let's go ahead and start. All right, here we go. So when last we met, we had a rule that said like dissolves like. Lena's computer's broken. Ah, bummer. Gosh, okay, well, I hope she can at least watch the live stream afterwards, the video. Thanks, Riley. And when last we met, we said that, what do we do? Heptane. We had heptane and it did not dissolve in water. So let's begin with that today. Heptane did not dissolve in water. And we want to answer why not. Well, first, there's Ali. Okay, good. Thank you, Ali. Good. First, I want to draw some waters. In fact, let's draw a big beaker. You ready? So here's our beaker. Remember, oil floats and so does gasoline. So here's the heptane up on top. Here's the waters at the bottom. So if they did not dissolve, then let's assume that the waters are being themselves, okay? So here's a water. And we learned that they're bent. So like that. And I'm going to guess, exactly, Shilpa, one of them's a dipole. Water's got a dipole, doesn't it? Remember that from last time? So I got a little minus and I got a little plus. And I won't put it on every one, but I'll put it on that one just to remind you. Well, if they're not dissolving in each other, so this would be the water down here, and this would be the heptane up here. If they're not dissolving in each other, then you know what? The waters are just liking each other. The waters are just liking other waters. So we're going to draw some waters around each other. So check this out. If that's an H, it's going to be interested in the next or if that's an O minus, it's going to be interested in another H, maybe here. You know what I'm saying? And same with this, this might be another O down here, right? And this could be another H maybe facing this way. Whoops. Excuse me. And so on and so on. So let's see, I could have another O maybe here attached to both of these guys. Now what I'm going to do is I've drawn lots of waters and I want to draw them kind of loosely connected. In other words, the O here will be interested in the H's, so I'll draw like a little baby line here, 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 and even here. And look at this, here. Okay, those little blue dotted lines, I'm going to bring you closer so you can see them. All right, everybody see my little dotted lines here? Those are all representing between the waters. So what are the waters attracting each other with? What sort of intermolecular force? What are these little blue dotted lines representing? Can you type in? What are the blue dotted lines representing that we learned about last time? Hint, H just likes to have fun, right? So we're going to say, aha. Waters just stay attracted to waters with what? Hey, several of you got it. Oh, man, good participation. Look at that. From Magdalena, Lee, Sarah, Chopin, Noah, Priya, Larissa, Riley. Thank you all. I'm glad you're paying attention and you got the concept down. So the waters are just attracted to other waters with hydrogen bonding. Hydrogen, if I can write it, bonding. So what's up with the heptane? All right, we're going to draw a couple of heptanes and see. Okay, so here's a heptane. 1, 2, 3, 4, 5, 6, 7, 8. Here's another one. 1, 2, 3, 4, 5, 6, 7, 8. No, not 8, 7. Sorry. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Pardon me, heptane. Okay, so I'm going to put the H's, imaginary H's around it. Remember, we don't put H, but we put dashes. That would be like single covalent bonds going out to the hydrogens, and so on. Okay, yeah, great. Now, heptane. Does it look like it has a dipole? And a dipole means one side of the molecule is pulling the electrons more than the other. Does it look like it has a dipole? Turns out, thank you, Natalie, Magdalena, Schopel, you're right. So there's no dipole. So heptane has no dipole. When does that happen? It happens when molecules are very symmetric. You see how I could like fold this on itself and it's the same? Same here. Whereas here I got an O side and I got an H side. It's not very symmetric, really. Okay, I got one side's more negative, one more positive. Here, both sides are pretty much the same. So we say it's a symmetric molecule. That often means no dipole. So what does it have? Okay. Exactly. The hydrogens encircle the C. That's right, Noah. Yeah. There is an attraction between heptane and heptane, but it's a different kind of attraction. And the waters, frankly, the waters are way too busy liking other waters. These guys are like, oh, I love you, I love you, I love you. They're like really, really getting into hanging out with hydrogen bonding, okay? These guys are doing something different. Remember we used the rule last time, like dissolves like? Like dissolves like. So I think already you figured out water. Dipole likes dipole, and especially this kind with O means it's hydrogen bonding, extra strong dipole, okay? Hydrogen bonding. But there is something going on up here, and it's something a little bizarre, okay? So bear with me. Imagine you're like some of the electrons in heptane. Let's say that just for an instant, more of the electrons in heptane are more at this side. Then just for that instant, this side's going to be a little more negative, and the other side's going to be a little more positive. But then it's gone. We call that a temporary dipole. Temporary dipole. It means it forms and then disappears right away. So I'm going to write heptane has temporary dipoles. Only. But let's do that again. You'll see. I'm going to play a little game with you. Let's say that just for a millisecond, okay, that side has more electrons. So this side's more negative. So they're missing from over here, so this side's more positive. Let's say that the next one over has exactly the same thing happen, except opposite. Let's say the electrons down here, by just for that second, millisecond, are over here. And then they're lacking over here. What that means is if it happens at the same moment, I get little attractions between the molecules. Oh, this side's more positive, this side's more negative on the other one, just for that moment. I'm gonna have you draw those attractions. The attractions are between weak temporary dipoles. Why does this happen, Noah? Because the electrons are in motion all the time, to be honest. We haven't talked about that, but I probably told you, well, they're right there between the two atoms, and that's it. And it's kind of true, but some of the electrons can shift around in the molecule, it turns out. So why? Because that's what they do, Noah. The electrons are in motion. And again, it's just kind of luck. So maybe then the next moment this disappears. But then maybe 2 moments later it reappears just for a moment. So has temporary dipoles only. There's an attraction based on temporary dipoles. It's not like this, where a constant attraction is happening with dipoles like down in the water. So a temporary, well, no, I don't want to say temporary attraction. Let's call it a type of attraction. A type of attraction is the result of temporary dipoles. Now I've run out of room and I have to tell you what that is. I'm going to do it up here. So can I put a little star here, folks? Sorry, I have to do it. You can just keep writing down there, all right? But for me, I got to write the rest of it up here. So that sort of attraction due to temporary dipoles is called London dispersion forces. I like the name. Dispersion means how they're arranged. If they're dispersed in a way where I got a few more extra here and in the next one a few more extra here, then there's a little attraction between the molecules. It's based on how the electrons are distributed or dispersed. The German name, by the way, London is not the place, it's a person who studied this. The German name for this force is named after a Dutchman who studied it. And the German name is van der Waals. Van der Waals, AA. Force, okay? Kraft. So if you have it in German next year, Leistungscourse course or something like that, then you'll be talking about van der Waals, but it's London dispersion forces. Okay, so it is. It's attractions between molecules. So let's call it the way they say it in the books. It's an intermolecular attraction. Due to temporary dipoles. Now, obviously, in this case, the hydrogen bonding down here is much stronger. And therefore, the waters are saying, no way, we're not playing with those guys. No, we're more of a team here. We're much more cohesive, right? Sticking together. And these guys up there then are just stick together because they're all they got. Okay. So it turns out waters have London dispersion forces too. They can have temporary dipoles too. But you know what? The actual hydrogen bonding is so much stronger that we don't really have to worry about that. But theoretically, they have London dispersion forces and hydrogen bonding between the waters. Here, it's only these, in this case, not as strong London dispersion forces. So like dissolves like. Dipole dissolves dipole down here. Non-dipole stays with non-dipole. Okay, that's what I mean by like dissolves like. Kind of weird, huh? So now I've given you three ideas. I can have dipole-dipole. I can have a special type of dipole-dipole called hydrogen bonding. And now I can have this third thing called London dispersion forces, which is where the molecules are very symmetric and it's only temporary dipoles that form. You might say, but temporary dipoles, why don't they like the real dipoles? Because they're not around long enough, folks, to attract to these guys. These dipoles come and go every millisecond, actually nanosecond. So it's not enough to break up these molecules of water and attract these guys to these. In fact, if I swirled it up like this, right? First they'd be mixed and then all the waters would come back together because they're more attracted to each other because they have permanent dipoles. Let's see if you have some questions. Exactly, Tadashi. The dipoles, let's say that they form and reform over and over. So temporary dipoles. So the dipoles form, disappear, reform, ... over and over, Tadashi. So it's just not a consistent force like it is with water. That's why they don't really mix. Let's see what else you ask. Okay, Larissa. Does this stronger attraction make water dense? Yes. Yes, Larissa. To be honest, You ready for this, Larissa? If there was no hydrogen bonding between water molecules, you and I would not exist. We're 90% water. If water didn't have hydrogen bonding, at room temperature, water would be a gas, and that is all. Isn't that bizarre? So it's because of hydrogen bonding that water is so special. Check out the periodic table. Watch this. H and O, right? What's under O? It's in the same group or family. It's S. Is there such a thing as H2S? There is, but it doesn't have hydrogen bonding. Why? Because S is not fun. It's not fluorine, oxygen, or nitrogen. So the dipole is much weaker. What about the next one down? Se, selenium. Is there H2Se? Yes. But the dipole is even weaker. So here's what happens. Weak dipoles, H2S, H2Se, H2Te, and so on, all those are gases at room temperature. The only one that has a strong enough dipole is H2O. That's strong enough to bring it together. And Larissa, it's bringing up together enough to make it dense enough to become a liquid. So Larissa, you're exactly right. Okay, so Dominic, you'll need to watch more of the video probably because I got to erase all this. And yeah, then you can send me your notes on it. Let's see, other questions. Magdalena. Heating water lessens the hydrogen bonding to an extent where liquid turns to gas. You guys are so good. Magdalena is exactly right. If I boil water, here I got some water here. I got something in it, but I'll tell you about in a second. But if I boil water, I've got to put in a lot of energy, to be honest. You remember I talked about the C value in physics of water being very high? I said there's really no other substance that the C value is so high to heat it up. Well, guess why? Hydrogen bonding. Now you know the secret of water. The secret of water is truly all about hydrogen bonding. And yes, there's a lot of heat I have to put in, Magdalena, to make it into a gas, to vaporize it. And that's why. I got to pull apart the magnets, right? Oh, they're not magnets, they're electrical charges. But still, I got to pull them apart to make them a gas. Good thinking. Any other questions or comments? You guys are red hot today. Freezing this water increases the density and the dipoles remain. Yine. When you freeze it, they become really rigid and they're in a certain structure, Lily. And water actually, you know how ice cubes float? That's weird. Most things when they become a solid are denser, but not water. You set up in another course. So the dipole's still temporary in frozen water. No, the dipoles are permanent even in frozen water, but there are other reasons that ice sets up a certain structure. But you may want to read that on the internet. It's beyond what we need to do for this course. But certainly the boiling is really important to understand. I got to pull them apart. That takes a lot of energy because they're attracted to each other. Ute. Okay, now. I want to talk about London dispersion forces a little more. Okay, turns out all molecules have London dispersion forces between them. I could tell you that they're all weak, but they're not. Sometimes, so these things, the London dispersion, sometimes weak, sometimes stronger. Now this will make total sense to you. Let's compare methane, and propane. Here's methane, right? Here's propane. Here's another methane. Here's another propane. Which would you guess? Just take a guess, everybody. Doesn't hurt to be right or wrong. Which one do you think will have stronger temporary dipoles? Methane or propane? Who will have stronger temporary dipoles and therefore stronger London dispersion forces? Methane or propane? What do you think? And the answer to your question, Magdalene, is yes. Which has stronger London dispersion forces, methane or propane? Make your guess. I got about half and half, huh? Well, it turns out the half that said propane is right. Stronger, I'm going to abbreviate this now. You're not allowed to do this on tests, but I've got to do it here because I'm running out of board space. LDF. Stronger London dispersion forces. Let's find out why. Okay. Well, they both can do this and make London dispersion forces, but it happens more regularly and with greater emphasis with propane because propane has more electrons. So it's more likely some will be on one side or the other. Methane has a whole lot less electrons. So I could have a little tiny plus and little tiny minus, but you know what? It's going to be pretty wimpy. And then it'll disappear right away. I still get a little London dispersion forces. There's my LDF. But you know what? I'm probably going to get more of them happening here because I have more electrons. And by luck, here I'll draw some. Let's say there are more at this end because I got more available, don't I? 3 C's and a bunch of H's. I got more electrons in the mix. So this side might be more negative. And maybe by luck, this sucker down here is more positive on this side and more negative at that same moment in time. Maybe the electrons are over here a little bit. Okay. So now I got more London dispersion forces. So here's my point. London dispersion forces get stronger. London, I'll abbreviate it a little bit, dispersion forces are stronger if I've got a couple things. If I've got more electrons, to make temporary dipoles, I'll write temp dipoles, DIP for dipole. And that's A. And then B, to be honest, it has to do with the surface area too. So this guy, the propane, has a greater surface area. Greater surface area. Can you read that? Kind of. Okay. So that's when your London dispersion forces get stronger. Who cares? You do. Here's why. London dispersion forces affect the properties. Guess who's got a higher boiling temperature? Methane or propane? Think back on what Larissa said a little bit while ago. Which one has a higher boiling temperature? So it takes more energy to break them apart. Which one has a higher boiling point, we could call it, right? And now everybody's given the same right answer, right? Magdalena, Tadashi. Let's see if some others have too. I don't have that data in front of me, but we can look it up somewhere. Methane, well, let's just say stronger LDF, so higher boiling point, BP, and melting point. Let me tell you what those are over here. So BP, BP. BP in chemistry means boiling temperature, boiling point. If you haven't had this before, and MP is the melting point. So you know what I'm talking about, okay? Of course, for water, the boiling point's what? 100 degrees Celsius. The freezing point or melting point is 0 degrees Celsius. That's what I mean by those temperatures. So it's a lot higher for propane because, here's the propanes, right? It's hard to pull them apart. Now, which has a higher boiling point, propane or water? Can you guess? You probably know already because you probably know what phase propane is at room temperature, right? Which has a higher boiling point, propane or water? Shall I write that as a question? Higher boiling point, water or propane? Water, 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 water. Lee is right, Natalie's right, Lily's right, Magdalena's right, Sarah, Larissa, Isabella, all right. Good. Because in this case, the hydrogen bonding is a stronger force between the molecules than the London dispersion force is here. Is it always the case? No. Okay, so I'll just write, yup. Stronger, here's a fancy word, intermolecular force. That's really what they call it in the business. Intermolecular force. Okay, let's do another kind of interesting thing. You probably know this already if you had me last year. C25H52. You know what that is? It's candle wax. It's the main ingredient in candle wax. But that's what, gang? That's a solid. But look how big it is. So I'm not talking about hydrogen bonding now. I'm back to talking about London dispersion forces. The London dispersion forces here are much what? If this is a solid at room temperature. And you know it is, right? Because we can buy candles. So compared to propane or methane, tell me about candle wax then. So it has London dispersion forces. Let's see if somebody said that. Stronger. Thank you, Sarah. Thank you, Noah. And probably others too. Not a big surprise, right? Aren't there more electrons than in propane or methane? Way more, right? And isn't it just bigger physically? Wouldn't it have a lot more surface area? It's a big molecule. Yeah. So not surprising. It's a solid at room temperature. The London dispersion forces are much greater. So they can be strong enough to make something a solid at room temperature. You just got to have a really big molecule to do it. This will become important when you and I talk about esters and fats later this semester. So I'm not doing this for fun. We're going to use this all real soon. Okay, let's see if you got some questions. Okay. Yes, Yain, Magdalena, be careful. So intermolecular forces are between molecules. So they're not bonds. Like a bond would be between, like, here's a water and here's an H and an O. So they're bonded together, but that's a bond. But between one water and the next one, that's hydrogen bonding. I know, I hate it. Or in German, Wasserstoffbrücken. Okay. And the other intermolecular forces, like between temporary, that involve temporary dipoles, those would be London dispersion forces. Or I could have just regular old dipoles and not have it be hydrogen bonding. At any rate, there's only about 2 or 3 types, Magdalena, of intermolecular forces. But there's 3 types of bonds, but that's between atoms. There's covalent bonds, ionic, and metallic. But that's where the atoms are stuck to each other. HO, they're in a molecule together. HO. That's not between water and another water. So this would be a bond between a hydrogen and an oxygen. And then over here, I got hydrogen bonding between the 2 waters. Does it stink? Yeah, it stinks. I hate the name hydrogen bonding. Can you tell? Okay. Because it's an attraction. It's not really a bond. Good. Anton, you're in the wrong time period. We're next hour. But thank you, Anton. We'll see you next period. Okay. Same as Magdalena's. Good. Okay. Then let's go to our demo for the day. You ready? Here's our demo. I know it's not the most thrilling demo. All right, you see it? Some of it's floating a little bit, but most of it's sunk. And most of the stuff I have in there is limestone. And if I put my finger in it and swirl it around, it's going to do nothing. And I want to find out why. Okay, so here we go. So my question to you is, well, we're done with this one now. Okay. So I had limestone, which is CaCO3, does not dissolve in water. Obviously, it didn't do anything. Why not? Salt dissolved in water, and this is another salt. Yeah, this is a type of salt. But NaCl did dissolve in water. So now I got to tell you, all salts don't dissolve in water. Why does this one not dissolve in water? Hint, what do you know? And if Anton is still here, he may know this. What do you know about calcium and what do you know about carbonate? Some of you may have something memorized that you know about them, and it's very important here. While you're doing that, I'm going to draw a little beaker. So here's my beaker. Here's my chunk of, I'll just put one chunk down here. There's my limestone. CaCO3. Okay, they have different charges. Yes, Tom. Now, Tom, what charges do they have? Different is not enough, but you're on the right track. What charges do they have? Yes, Lily, that's correct. Yes, that's correct. Okay. What charges? Yeah, thank you, Tom. Good. Very good. Okay, now, here's the deal. Ca is 2 plus. Let's draw some of these. Ready? Ca is 2 plus, and I'm going to put it next to a carbonate. That's a lot bigger because it's negative. Usually the negative ones are bigger. CO3, 2 minus. There's another one, Ca2 plus. And there's another one, CO3, 2 minus. And I could put another one up here, right? CO3, 2 minus. Could I do this all day? I sure could. Ca2 plus. Why is that charge important? Here, I got waters, right? I got H2O. And I got a negative end and I've got a positive end. Remember with NaCl, the Na plus like the negative end, the Cl minus like the positive end, right? I'm going to put this and then I'm going to erase it. Okay, Cl minus like this and Na plus like this side. But that doesn't happen here. Why not? What's the deal? Because Tom said that these charges are 2 plus and 2 minus instead of NaCl, which is 1 plus and 1 minus. Why does that matter? And it does matter. Do some thinking, folks. Why does that matter? Why is Tom on the right track? It's not really about a different amount of electrons. You figured out the reason. I just want somebody to say it in words. It's 2 plus. Look at this. This is 1 plus 1 minus. This is 2 plus 2 minus. What's the limestone going to do, gang, that the table salt is not going to do? Larissa, because the attraction is stronger. Ta-da! So, thank you, Larissa. Hey, 2 plus is way more attracted to the 2 minus here. So it's just not interested in water's dipoles. Sorry, water. So CaCO3 stays together. The water is not strong enough to like pull it apart, so to speak. Or to put it another way, this bond, and now we're talking about an ionic bond, right? Because these are ions. So the ionic bonds here, and I don't mean in general, I mean here in calcium carbonate, are stronger than the attraction to water's dipole. How can I fit that in there? How about are stronger than, how about I say hydrogen bonding? It's not really the case though. No, that's crappy. That's really crappy. The ionic bonds here are stronger than any attraction to water. That's really the right way to say it, okay? So see if you can write a little bit of that. I'll try and read it. I'm sorry it's all over the place. So the NaCl did dissolve. Here, ionic bonds here, and I'm saying here all of these ionic bonds, they're stronger than any attraction to water. So the calcium carbonate stays together. It doesn't mix with the water. So there's no ion dipole force here. It's just the ions are bonded to the other ions and they're staying that way. Sorry, water. Questions from you? I'm going to send you an assignment to start to do some drawings because you know enough to do this. Okay? Exactly. The attraction's stronger, right? So, yeah, okay, good. We saw that already. All right. So I'm going to have you try some drawings and then we'll talk more about alcohols and stuff real soon. Okay? Good. Thanks for your participation. Our time is over. I'll send this on for those that were late and those that weren't here to the live stream. Bye, folks.